Welcome back. This is another concept problem video. In today's video, we want to find the voltage across resistor 2. So we want to find a voltage R2. So polarity, we're going from minus to negative on our voltage source. So we're going to go plus to minus, and we're going to go plus to minus. We're going to call this VR2, and we're going to call this VR1. Let's put a node here. And that node is VR2. So that's the voltage across R2. So we can find the voltage drop or the output voltage. So in a sense, VR2 is V out. So we can find the voltage drop or the output voltage of the following circuit using Ohm's law. We know that the output voltage needs to be a function of the I, R1, and R2. So V out is a function of the input voltage V1 and R1 and R2. So with Ohm's law, we know that V is equal to I times R. And we know that the resistance seen by the voltage source is the sum of the resistance in the circuit. So we know that R, let's just put that in black too. So R is equal to, well, we could call that R equivalent is equal to R1 plus R2, which is the sum of resistance seen by the voltage source. So, because V is equal to I times R, we know that the source voltage, V1, and let's just call it V. Let's call it V. So for this, we're going to call this V. So let's call this V. So V is equal to I times the sum of resistance, which is R equivalent, as equal to I times R1 plus R2. So we can call this equation 1. We also note that the voltage across R1, is not relative to ground. The voltage across R1 is relative to the voltage source and the voltage drop across R2. So the voltage across R1 is equal to the voltage of the voltage source minus the voltage across R2, which is equal to V minus V R2, or that's equal to V minus V out. So the voltage across R1 is equal to the voltage of the voltage source minus the voltage of the output. So it's just the difference across the resistor R1, and we can call that equation 2. So when we look at the voltage across R2, we see that that voltage is the difference across, well, is the difference of the voltage drop across R1 and ground, which that would be the voltage across R2 and ground. So that's the difference between this point and this point, and the voltage at this point is VR2. So then that voltage, which is VR2, which is equal to V out, is the difference of V out minus 0. That's 0 volt, because that's ground. So remember, we can call, let's write that in blue, this point right here, VR2. Well, actually, it's already here. So VR2 is equal to V out. So this point is either V out or VR2. And that voltage is basically the difference between this point and this point. So that would be V out minus 0 volts, which is equal to V out. So the voltage across R2 is V out. So then VR2 is equal to V out. So we can call that equation 3. So from here, we have 3 equations to choose from. Thus, we also know that V is equal to I times R. Thus, we choose 2 equations that contains the quantities of interest, or the quantity of interest. And the quantity of interest is basically voltage across R2. So if we see, or if you think about it again, V is equal to I times R. We look here, the quantity of interest is VR2, and we know it has to be a function of V1, or V, which is the source voltage, R1 and R2. Here we see we have R1, R2, and we have V. And we know that in order to get the voltage, we need I, and we can see we have I here. So we have all 3 quantities here, and the I that we need to multiply times the resistance to get the voltage. So we can write that, or we can just go down here and just say equation 1 and equation, that was 3, equation 3. So that gives us equation 1 is equal to V times I. V equals I times R, which is the sum of the resistance seen by the voltage source. And V out is equal to VR2. So the voltage source is equal to the current, the input current, times the total resistance seen by the source, the voltage source. And the voltage across resistor 2 is equal to V out. So we need to find the voltage across R2, which that is called V out. So V out is equal to I times the resistor R2. And we know that I, if we manipulate this equation, I is equal to V divided by the resistance seen by the voltage source, which is R1 plus R2, and we multiply that by R2. So here we see that the output voltage, or the voltage across R2, is equal to V times the targeted resistance. So the resistance that we want to know the voltage drop across, divided by the sum of the resistance seen by the voltage source. So that becomes R1 plus R2, and we can just write that again we can write that as the resistance of interest. So we're going to call that the load resistance, RL. And we're going to call this the total resistance. Normally that's writing R equivalent, seen by the voltage source, all over REQ. And that is the voltage across the resistor of interest. And that is a voltage divider equation. So we have here resistor of interest, total resistance seen by the voltage source itself, and that gives us the voltage across whatever you need. So again, we know that in a series circuit, the voltage is divided up by the resistance.
In a DC circuit, voltage equals current multiplied by resistance.
Okay.
This is from Wikipedia.
Okay, Siri. Never mind. Bye. Okay, so basically what I was saying is that the voltage the okay, so the in a series circuit, the voltage is divided up amongst each resistor. So therefore, when we need to find the voltage drop across a resistor in a series circuit, we need a voltage division equation. In a parallel circuit, the voltage across each resistor is the same, so therefore we don't need to use a voltage divider equation. For that, we need a current divider equation because the current going into a parallel circuit of resistors or a parallel combination of resistors is divided up between each resistor. So for those, we need a current division equation. And for voltage with a series circuit, we need a voltage divider equation. So I'll see you in the next one. Bye. Siri.